There we go. All right. Really quickly, I realized I forgot to post the slides, so I will just put those in the Zoom chat. And if anyone asks for them because they joined late, feel free to just repost it for me. Thank you. And I'll make sure I get those posted by the end of section. But yeah, so today is about two of the more, I don't want to say more important, all of these protocols are important, but the ones that are more relevant and the ones that we get into on a deeper level when it comes to computer security. So these are TCP and TLS. Again, I know the networking module is just full of acronyms, but we've got to go with it. So going into, actually, before we go into this, does anyone in person or online have any questions on anything that was covered so far? Yeah, Zoom chat is. Oh, I should probably share my screen. Okay. Great. And I did get some feedback in the mid-semester surveys that I was not paying very much attention to the students online. So I promise I will do better at making sure I'm polling both in-person and online students. But yes, that was something that someone brought up and I wanted to make sure I address that. But yeah, going straight into TCP, this stands for the Transmission Control Protocol. It's the main protocol that is used on the internet when we want to send data from one place to another. So it provides a couple of things, a couple of useful abstractions that we don't get from just standard IP. The first thing is reliability. So whereas when you send raw IP packets, that's considered best ever. So it's basically, I promised I will do my best to deliver it, but I provide no guarantees that your data will actually make it to the other side. TCP, on the other hand, provides reliability. So it means if you give me data, I will get your data to the other side, unless the entire connection crashes, at which point there's nothing to do. It also provides something called port numbering. So if I have two services running on a computer, let's say I want to host a web server as well as an SSH server, as most of the computers in the hive do, then we have to have some way of differentiating. I'm addressing the web server versus the SSH server. So these are called ports. Every computer only has one IP, but it can have any number, well, it has, if it's 2 to the 16 ports that you can use to address different services on that computer. There are a couple of common ports that are used for different protocols. Usually we use port 80 for HTTP, 443 for HTTPS, and so on and so forth. You don't need to remember these, but they're good to know if you ever get deeper into networking stuff, or if one day you have an error that says like port 80 crashed or something, and you can just memorize it off the top of your head. This is an example of what the TCP handshake looks like. So we've got everything above here is considered the handshake itself. It's called the three-way handshake because there are 3 packet pillars that have kind of the handshake. The first is SYN, stands for synchronize. Basically says, hello, I would like to initiate a TCP connection, and I'm going to start using this sequence number. So remember that because TCP provides ordering or as well as reliability, it needs to have some numbers attached to its packets so that you can reorganize the packets when you receive them out of order. So it says, hello, I would like to synchronize that sequence numbers. I'm going to start with X. The server, if they choose to accept this connection, they're going to say, okay, I want to synchronize my sequence numbers. I am Y, and this packet is also an ACK packet because I received your sequence number, and I am acknowledging X plus 1. So whenever we acknowledge, we always acknowledge the number after what was most recently received. Finally, the client, because it received this in, it has to complete that ACK. So it says ACK, I got your sequence number, you're going to be starting at Y, and I'm acting with Y plus 1. So now both the client and the server know each other's sequence numbers that they're going to be using, and they can start sending data. So let's say, oh, the client is, I'm going to send 2 bytes to the server. Here's some data. The sequence number is X plus 1, because that I already used X. And then the server knows that X plus 1 and X plus 2 are these 2 bytes here. So I'm going to act the next one is X plus 3. That's the handshake and protocol at a high level. Any questions from anyone? The sequence numbers are there to avoid replay attacks, right? Yes. There are multiple purposes to it. The main one, I would say, is to be able to reorganize the packets. So let's say I received packet 1, and then I received packet 3, and then I received packet 2. Because they have sequence numbers attached to them, I know, oh, this is actually goes over here, and then I can return the data in order to the application. But you're right that it does also prevent different kinds of attacks. I wouldn't say replay attacks, because if an on-path attacker wanted to replay data, they could just inject into that connection the replay data. But in something like TLS, the record numbers are definitely there to avoid replay attacks. Speaking of attacks, we should always assume that the attacker knows the source IP, destination IP, and destination port. These are just kind of general assumptions. I know this is your address. I know that you're speaking to the web server at Google. So I know Google's address, and I know you're using port 80 or 443. The first attack that we talked about in lecture was some kind of data injection. So going back to here, what we really need to send a packet is we need to know what the sequence number X is, and then we can inject our own data. So if I know that the client's initial sequence number was X, I could forge a packet saying, hey, here's some malicious data. The length is like 10, and I'm going to start a sequence number X plus 3, because I can see these sequence numbers here, and I know the next unused one is X plus 3. That's data injection. You need to know the sequence numbers, or you need to be able to guess them in order to spoof the packet. And if you're an off-path attacker, then you can't do this. So generally, we consider data injection to be difficult for an off-path attacker. Difficult in that it's not really feasible for them. The same goes for reset injection. Basically, instead of data, you inject a packet that says, abruptly terminate this connection, no more data is going to be sent. Again, you need the sequence numbers in order to spoof a reset packet, so you can't do this unless you're an on-path or man-in-the-middle attacker. And finally, we have some kind of blind spoofing. So let's go back to the handshake again. If I want to pretend to be the client, I can say, okay, here's a fake synchronized packet with the attacker's chosen sequence number. The server is going to say, okay, here's my sequence number at the malicious sequence number. But because it was spoofed from the spoofed to look like it's coming from the client, that's going to get sent to the actual client. And then if the attacker can see, oh, I see the server use sequence number Y, then I can inject an ACK packet to finish the three-way handshake, and then inject data before the client realizes, hey, I received a SYN-ACK packet without sending a SYN, something weird is going on, and the client's going to reset. So for these blind spoofing and blind injection attacks, you need to be able to know what the sequence numbers are. All right, questions? All right, the first question is about TCP, but I want to wrap up UDP really quickly because it's really simple. It stands for User Datagram Protocols, datagram protocol. Datagrams are really just messages. So I can send you a message, and that one packet containing a message is considered a datagram. It's a very thin wrapper outside of TCP, and really the only thing it provides is ports. So the only reason this exists is because a server can have multiple UDP services. So maybe they have a DNS server as well as a video live streaming server. And both of those will use UDP, but they use different port numbers. This is the most useless diagram you'll probably see in this course. If you have UDP, you send data, and that is it. Yeah, that's pretty much it. Because it's so simple, there are a number of attacks on it that are all the same as IP. Basically, you can do anything because if you have the source address and the destination address and the destination port, then you can just send data from anywhere. So we're really going to say this is easy for an attacker, and we're relying on higher layers in order to actually defend against other attacks if they need those defenses. All right. So let's get into the discussion sheet. I apologize. I know it says Weaver Fall 2020. I just like to pretend 2020 never happened, which is why we get this. No, it's not. But yeah, so this
I
was
never read full 2020 when I'm like, oh, aren't we at full 2020?
yeah. So if we just pretend 2020 didn't happen, this discussion should
I
be
think every person agrees full 2020 never happened.
pretty much.
Pretend like it's never happened.
Yeah. So this first question is a pretty conceptual walk through TCP, basically saying, what should the sequence numbers be for the different packets and what can on and off path attackers do to this kind of thing. So it's not too difficult. Why don't we take like 5 minutes to do this question, and then we'll come back and talk about it. And if anyone in person or online has questions, feel free to ask.
So A plus 1 will be included in this part of the LA, right?
Yeah, so we're saying, this packet contains LA bytes, and the bytes they represent are sequence numbers A plus 1 through to A plus LA.
Okay, got it.
Yeah.
So A plus 1 plus LA is the beginning of C.
Yeah, it's the beginning of C, and that's why that's where this packet gets its sequence number from its first byte. Like that. So sort of extending this logic, we've got data D going from the server to the client. All right. So going by that logic, what should the sequence number of data D be?
B plus 1 plus LB.
Right. B plus 1 plus LB, because that's the sequence number for this first byte here. Now, the ACK number is always the one that has been most recently received by the server. So we're assuming that A and C are already, that the server already received data A and C going from the client to the server. And the ACK is the one that is expecting next. So what should the ACK number be for this packet? What should the act number be here?
A plus 1 plus L, A plus LC.
Exactly. Yeah, A plus 1 plus LA plus LC. Because the server is acknowledging I've received A, I've received C, and the next one I'm expecting is this one that I haven't received yet. So that's what goes in the act number. If the server had not yet received C, let's say that got lost in transit, then the act would still be A plus 1 plus LA. And then the client would know, oh, something has gone wrong. I need to retransmit this packet. Go child, and make sure I can see it. All right. So now we have the two types of attackers the two main types of attackers we'll talk about in TCP, on-path and off-path attackers. And also, yeah. So I know the formatting is really weird, but question B goes all the way to its own page. So probably killed an entire tree just to print this question. If Carol is an on-path attacker, what kind of thing attacks can she execute on TCP? Just shout out their names if you remember, or you can describe them as well.
Can you exclude the sequence numbers?
Can you what the sequence numbers? So I'm not quite catching that word.
Spoofing.
Spoofing. Can you describe that a little further?
I don't remember exactly, but like you can if you can find the sequence number and like pretend you're the client.
Yeah, exactly. So let's say I want to spoof some data from the server to the client. I'm going to say, oh, my malicious packet is M. Written in really poor marker, so let's just say it's M. I know that the server is expecting the next sequence number in this case to be B plus 1 plus LB LD. So I can set, actually this would be from the server to the client. So I can inject a packet into the connection that has some malicious data in it. Yeah.
So it says here, Carol's an on-path attacker. And so are like all attackers able to generate their own like traffic?
So all attackers can try, but off-path attackers won't be able to see these sequence
On-path
numbers,
attackers
right?
need to guess all this.
Right.
Okay,
So they can still send a packet, but it would probably just be wrong.
So on-path attacker, they observe, can't modify any existing traffic, but they can create traffic.
Right, exactly.
Okay, and man in the middle is observe, create, and modify.
Yes, exactly.
Got it. Thank you.
So the on-path attacker, basically you've got communication going on here. They would inject their own packet in here before the client's next packet arrives. So they would receive, sequence number equals X. This is also sequence number equals X. The server will receive the real one from the client, go, oh, the client must have just retransmitted this because they didn't get my packet, and ignore the data the second time, even though this first packet was actually injected by the attacker.
And it doesn't necessarily have to be like injected like for a packet to the server, right? But also
Yeah, it could go.
send it back to like whoever's sending the client. Like Carol can also like send a response to the client as long as it reaches that, as long as it reaches the client before the server.
Yeah, as long as the sequence numbers are what the party is expecting. So for the client, they're expecting packets with like B plus 1, B plus 1 plus LB, and so on and so forth. The server is expecting A plus 1 plus LA, and so
on. Okay, so let's say the client received like a Carol's packet, right? Before like the servers. So when the client do see the server's packet, does it just ignore like the message that is being sent along with it?
when it receives a packet that thinks it's a duplicate, so let's say it's a client here, the server here, the attacker injected data right here, and then the server sent its actual data later. So this has sequence number Y, this is also sequence number Y. The server receives it the first time, checks, oh, the sequence number is right. So I'll just take that data, pass it to the application. And then it'll receive a packet again. The client says, oh, that's weird. Well, it's not that's weird. Oh, I received a duplicate packet. It doesn't actually check like the contents match what it was passed to the application because it doesn't remember it. And then it'll just think, oh, I received a duplicate packet. I'll just send the app again because maybe that's the get.
So the client and server only keeps track of the currency, not like the content.
Exactly, yeah, because all TCP is doing is passing the contents to the application.
Okay. So it would resend, like, it would assume that the act was lost and just resend the
Yes,
packet again, right?
yes. Exactly. All right. I'm going to skip over the off-path attacker stuff because we already talked about it. Because I do want to get into TLS, but very briefly, there's not much that David can do because David's off-path and doesn't have these infrastructures. All right. TLS is this other protocol that we talked about, and it's that magical protocol we keep talking about that provides security that the lower level layers can't provide. So it stands for Transport Layer Security. Probably wait till I actually get inside. It stands for Transport Layer Security, and it's essentially a transparent layer over TCP. So TCP provides this stream protocol. You know, we send bytes in and we get bytes out. And with the other direction, and TLS does the exact same thing. So I send a stream of bytes into TLS, and out the other side comes the stream of bytes that was passed through TLS. The key difference is that it's encrypted and mapped using cryptography. So we have confidentiality. We don't learn the contents of the byte stream. We have integrity. The attacker can't tamper with the byte stream. And we have authenticity because we're going to be able to identify the server using their certificate. So this is a diagram of what the TLS handshake looks like, and we spent a lot of time in lecture going over it, so I'll try not to go into it too much. Basically, we have two hellos, which are just hello, which is a connection. They both contain a random number that is chosen by the party that sends it. The server is also going to send their certificate at the same time. In RSA TLS, which is the first of two variants we talked about, the client chooses something called PS, which stands for pre-master secret, encrypts that using the public key embedded in the certificate, and sends it to the server. The server is going to, and then both the client and the server are going to send max over this entire dialog. So we derive the key using the two random numbers here, as well as the encrypted pre-master secret. That's how we derive our keys, including IKS and IKC. And then finally, we map this entire communication just so we know the attacker didn't tamper with it. These three parts, RCRS, client random, server random, and pre-master secret, are going to be important because we're going to do the same thing, but with a slightly different handshake. So this was Diffie-Hellman TLS. The main change is right here. So instead of just encrypting, instead of, instead of just encrypting a pre-master secret and sending it over to the server, we're actually going to do a Diffie-Hellman in order to derive the pre-master secret. So it's the same G to the AB mod P. When the server sends its like pile of data, it includes a signed G to the A mod P. And the client will also send a G to the B mod P. Notice that the pre-master secret is never sent as part of this handshake, but it's derived independently by both the client and the server, which gives us the additional forward secrecy, perfect forward secrecy property that we talked about. And then everything else is the same. We've got our max at the end, we've got our client below and certificate at the beginning, and so on and so forth. And that's all I really wanted to talk about because we're going to walk through a couple of attacks on this discussion here. So first question is some conceptual stuff about TLS, and then with luck, we'll be able to get through questions. We'll see. So why don't we spend like 5 minutes on this, and then we'll talk about it, and then we'll go straight into questions. I just realized the camera was not pointing at the screen, so that's all everyone saw was just me probably stepping in and out of the frame, but it's okay.
When is the key used for the map generated?
It's derived really as soon as possible. It's derived from RCRS and the tree master secret. Once we have those, we can derive the master secret. And from the master secret, we derive 4 keys, including IKS, I think.
So it's like similar to like the one in the project where we using a key to derive like.
Exactly. It's actually done exactly with a key derivation function. Right. All right. So the first of all question we were just talking about the protocol. What are the reasons why we include both a client random and a server random as part of the generation of our secret? Or what's the point of using generate?
We used to generate master secret.
Okay, but we do already have this pre-master secret that has its own, maybe better in the RCTLS. But we have this pre-master secret, which the attacker can't, because it's encrypted with public key. So why else, what might we want to include some random fields in here?
Like, so going back to the pre-master secrets, but although the attacker don't know what it is, they just tamper with it, right?
Sure they can, but if they tamper with it, then they'll derive different keys, and then when they send the maps, they'll notice that the dialog will change.
Right.
So it's not just a matter of tampering with the connection. Let me ask you this: if let's say that we recorded this entire connection,
Mhm.
and then later on we were able to recover what the value of the master secret was here. Is there any way, and let's say these random fields don't exist, and just the master secret is the pre-master secret. Is there any way I can force the server to derive the same master secret as last time, if I had already recorded the previous connection?
It will always derive the same master secret because the public secret, the shared PS is like, should always be the same. It'll be like the same master secret for every client server pair.
Yeah. And Julius Online is sort of, I think, is also getting at a similar point of preventing replay. If I record this, I don't know what the value of the pre-master secret is, but I still have this ciphertext. If later I impersonate the client, and or not even impersonate the client, but I perform some sort of on-path injection, I send this pre-master secret again, the server receives this, they're still able to decrypt it because it's the same thing as last time. And then they'll have the same pre-master secret as before. So the idea of including random fields chosen by both the client and the server is that even if just one of these elements is random, or we're incorporating random elements from both parties, so that the attacker can't just replay the connection from one side and result in the same handshake. Because it's very dangerous if they're able to trick the server into completing a handshake. But we mitigate that if both the client and the server choose random values that are incorporated into the handshake.
So would there be a new random like RC and RS for every time that client attempts a connection?
Yeah, pretty much. So let's say I recorded the client side of the connection and I'm impersonating the client. Even if I send the same RC as last time, the server still chooses a new RS. Same thing with the server. If I impersonate the server and send in the RS, the client will still have chosen a different RC. And impersonating the client and the server isn't really interesting because then you're just both sides of the connection and you can do whatever you want. So that's the point. We're really just incorporating randomness from both sides to prevent replay attacks. Client and the server hello, we sort of talked about it already. These aren't encrypted or authenticated, but that's fine because these are public values and we have this backend here that's authenticated. It's not too important, and again, it's really just there to prevent replay attacks.
So if like, so the man in the middle can they still like attack while the client server is like they're connected, right? So why couldn't the man in the middle use the RC and RS to also generate like the same key?
Okay,
And
yeah.
also like use that to like attack while like in the same connection. But I know if it's like I know if the man in the middle wants to start another connection with the server and impersonate to be the client, that won't work because the RC and RS is going to be different. But why can't the man in the middle just do like the attacks while those two are connected?
Yeah, so that gets into that third part here, pre-master secret. It's called secret because any attacker in the middle won't know what the value of the pre-master secret is. Notice that here it's encrypted with the public key of the server. And in here, the pre-master secret is derived from the 50 element. So in both cases, anyone listening in on this conversation doesn't know what the pre-master secret is. Does that make sense?
Oh, okay. But maybe like what I am kind of confused about is like earlier we say if we don't have RC and RS, then the attacker could like replay the connection by just giving the pre-master secret. So in that case, are we assuming that if the pre-master secret leaks, then we would have like a problem? But
Yeah, the danger is really more just if that you're able to trick the server into reusing the same key.
Mhm.
Because we've also got like other issues with if we use the same key across two connections, that there are also cryptographic issues there. So what we want is we always want random elements chosen from both the client and the server.
Yeah.
Very good question. All right, so one question that gets asked pretty frequently, and that we're asking in this discussion is that there are two sets of keys. We've got in one direction CB and IB for confidentiality and integrity. And in the other direction, we've got CS and IS for confidentiality and integrity. So the browser here is a server here. Why might we want to use different keys for each direction? What's an attack that might be possible if we use the same key for both directions? Let's just say there's just two keys, C and I. We send an encrypted message, and over here we send another encrypted message. And these are all also authenticated. What might be the issue if we use the same key in both directions? What could the attacker do?
Is this something that we're using keys?
A little bit. So if I took this message and sort of flipped it around and pointed it back this way, what is the structure of this message? Well, it's still some message that's encrypted using the key that it's expecting, using this key C. And it's also going to be authenticated using key I. So what I can do is I can trick the server into thinking the client sent a message that the server sent itself. Now, you might imagine that in most cases, maybe this isn't much of an issue. But again, the idea is we can't tell if the server or if the client actually chose to just reflect the exact same thing back to me, or someone executed this, reflection attack is what we're going to call it. So if we change the keys in each direction, let's say this is CB and this is CS, then when we try to execute a reflection attack, we turn this back around onto the server. It'll see, oh, that's weird. It's encrypted with the wrong key. Or in reality, what it's going to do is it's going to attempt to decrypt it with CB as it's expecting and just get garbage.
Wait, why is the reflection attack like how is it like considered an attack? Is it just
Well, the idea is we want to be able to distinguish if an attacker is tampering by connection, right?
Mhm.
So if they are able to reflect our own communications back at us in a way that we can't tell if an attacker did this or the client genuinely meant to reflect my own response back to me, then that's a loss of integrity.
Oh, okay.
So if we use different keys for each direction, that prevents this attack. And that's why we generally say one key per purpose. Quick question. If an attacker succeeds in executing a replay attack, the attacker will be able to decrypt past communication it may have recorded correct. It's not quite a matter of being able to decrypt past communication. It's, again, the idea of integrity. We can't tell if the client meant to send the same thing twice, or if an attacker just replayed their thing. You might imagine that a request that says, send Mallory $100, if you can repeat that request over and over and over again, that's a bad thing. So we want to make sure that replay is not possible. So you might have noticed that one thing is missing from here if we are to defend against replay attacks. What additional piece of data might we need in order to fully prevent against replay attacks? Not just the message itself, but what might we want to include with the message?
Like a sequence number?
Yeah, exactly. So maybe message concat 0, concat 1. This is a very informal way of doing it. Also very messy way of doing it. Sorry about that. And the idea is now, if an attacker tries to replay the same message, just copying this over, then they'll receive it and go, hey, hold on, I already received a record with this number. Someone must be executing a replay attack. So we need, they're called record numbers in TLS, but we need additional record numbers in order to fully prevent against all the attacks. So multiple keys to prevent against this reflection and record numbers to prevent against replay. All right, we don't quite have enough time to go into this last question. Let's see. All right, I'm going to give everyone 1 minute to look at this question, and then we're going to speed through it. Let's see. All right.
Certificate.
Certificate pinning, we didn't go over it. I think it's a relic from when we used this before. It's basically saying instead of trusting any certificate signed by any CA, trust like this very specific certificate and nothing else, even if it's signed by others. But you don't need to worry about it. Very much. Fascinating. All right. All right, really quickly, which of these attacks are possible if somehow the attacker manages to get a copy of a web server certificate?
Personally,
Certificate?
yeah, if they have like the copy.
So, do you remember what the certificate contains? The certificate is just a signed attestation of someone's identity, right? So it might say Google's public key is, and then whatever the public key is. That's public knowledge, right? Yeah. So I receive a copy of Google certificate every time I go to google.com. Does getting their public key give me an advantage?
No.
Right. So it should be right, none of the above. No, no, no. All right, what if we get the private key of a certificate? So there's some CA out there who everyone trusts, and we get their key. What could we possibly do?
Could discover things that's what previous said. Yeah.
So that's, remember, we have this certificate here that's for Google, right?
Mhm.
And then we have some CA certificate here. Which private key did we use to encrypt the pre-master secret? Or which public key did we use to
The
encrypt the
server
master
is
secret?
public key.
We used Google public key, right? Because they sent us their certificate, we checked their certificate, that contains their public key,
Right.
and then we send the pre-master secret encrypted to them with the public key. So if we compromise this CA, that doesn't give us Google private key, right? So we know they can't break, we're going to call it perfect word secrecy. Can they impersonate? And it's so hard. Sign your own, exactly. So if I have compromised the CA, I'm just going to create my own certificate that says, people. Oh, that's terrifying. It's like, oh, this is also for Google. And everyone trusts this because they trust the CA. So we can't impersonate. And what about replay attacks? Nope. Nothing about this changes replay attacks because past connections or all connections always use different numbers. All right. What if they obtain an old certificate from Google? So it's a revoked certificate. Yeah.
Won't be able to impersonate.
So no impersonation. No one trusts this certificate anymore. What about breaking perfect word secrecy?
Because
Diffie-Hellman.
we're using Diffie-Hellman, I don't think it matters. So it's like, no.
Right, exactly. So this is Diffie-Hellman, so no. Replay attacks, just speeding through it, same thing, can't do it. Now, if they, now we're using RSA TLS instead of Diffie-Hellman TLS, which are the, we know replay attacks are possible. And they get a current private key. What can they do?
They could impersonate because they have the private key of the CA.
So they actually have both private keys, so they could also use Google private key directly, but in both cases, they can impersonate Google. Can they break the secrecy of past connections?
No, because oh wait, they're not using different.
Right.
Yeah.
Right, so they recorded this, they can now just decrypt this and direct master secret. So with R, so these three are Diffie-Hellman. There's a RSA.
Why can't it be the replay?
Replay it. Let me double check that. Yeah, replay attacks still aren't possible. Just because in TLS you have those record numbers all the time.
Wait, what?
You always have record numbers in TLS, so you can't ever actually do a replay attack
Oh,
because those record numbers are always
like, okay, so like the sequence from the previous one, right? That kind of like.
Yeah,
oh, this
yeah.
record has like this number.
there.
Would it not be possible for the attacker to just change that record number, sequence number to be like the newest one?
So let me double check this.
Like if the
Oh, this was a previous connection, so it's actually talking about the random numbers here. Even if we compromise the private keys, the client or the server or the client's still going to choose its own random number each time.
oh, okay,
So we can never reach. Yeah.
got it.
So replay attacks are never possible because we're always choosing random numbers. All right.
But if it's like the same connection, if the can't have the man in the middle, because the man in the middle could see like
Yeah.
every single record, right? So let's
Right.
say the most recent record is like 10, and I want to like resend like a previous record that's like record 9. Can I just change that 9? Can I just like copy everything except the sequence number and change the sequence number to be 11? Because
Yeah.
the man in the middle knows that information. Right?
Yeah, I would say that's more just impersonating the server. Because replay attacks are more like you're playing from the past connection. And I realized in the last question we were talking about replays within a connection, but this question is asked about replaying a different connection into the current connection.
I see.
Or as a replay.
Thank you.
Yeah. All right. Any other questions for anyone? I know we're 5 minutes over, so feel free to leave, but make the question if you have any. All right. Thanks everyone for coming.
Thank you.
All right, stop recording.